And now in this lecture we find out the area of the green shape. In the drawing we have square ABCD. We know that one side of this square ABCD is equal to 10 units in its length. Inside this square we have a quarter circle and this semicircle. Again, our task is to find out the area of this green shape. So first of all, we find the center of this semicircle. This point is point O. BC is one side of square ABCD, but BC is also the diameter of this semicircle, and it is equal to 10 units, and therefore the radius of this semicircle must be equal to 10 over 2, that is 5. So the radius OB equals to 5, and the radius OC also equals to 5. A is the center of this quarter circle, and so point A is the center of the quarter circle, point B is the point of the quarter circle itself, therefore AB is the radius of this quarter circle, is equal to 10 units in its length. AD is also the radius of the quarter circle, is equal to 10. We define the intersection point between the quarter circle and the semicircle. This point is point M. The next step, we join points A and M together by straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself. Therefore, AM is the radius of this quarter circle, is equal to 10 units. Actually, AM is tangent to the semicircle at point M. We join points O and M together by straight line. Point O is the center of the semicircle according to our definition. Point M is the point on the semicircle itself. Therefore, OM is the radius of the semicircle. That is equal to 5. The radius OM is equal to 5. The radius OM of the semicircle is drawn to point M. That is the point of tendency of tangent AM in this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular. Tangent AM will be perpendicular to the radius OM. If AM is perpendicular to OM, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points A and O together by straight line. We know that all the angles inside the square are right angles. So this is angle ABC, that is one out of 4 angles of square ABCD, and therefore it is a right angle. In the next step, we'll implement the Pythagoras theorem on this right triangle, triangle ABO. So it could be the right triangle ABO. In the equation, we'll implement the Pythagoras theorem on this right triangle, triangle ABO. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for whatever theorem. Okay. This is the right triangle ABO that are coming from the original domain. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I write it down. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so leave it as it is. So it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, AO squared equals to 100 plus 25, that is 125. So AO squared equals to 125. We substitute 125 by 25 times 5. So AO squared equals to 25 times 5. Here we take a root out of this equation and we get that AO equals to the square root of 25 times 5. The square root of 25 is 5, so inside the root we left only with 5. So in total we should found out that AO equals to 5 times square root of 5 units in its time. AO equals to 5 times square root of 5. So actually, this is side AO is equals to 5 times square root of 5 units in its length. Actually, those two right triangles are going to each other according to side rule. So I prove that the right triangle ABO can go into the right triangle AOM according to side rule. This is the right triangle ABO. We have to prove that it congruents to the right triangle AOM. This is the right triangle AOM. According to side rule. So why those two right triangles congruent to each other? First of all, AM equals to AB equals to 10. Side AM of the right triangle AMO is equal to side AB of the right triangle ABO. AM equals to AB equals to 10. They're both equal to 10, therefore they're equal to each other. In addition, side OM of the right triangle AMO equals to side OB of the right triangle ABO. Again, side OM of the right triangle AOM equals to side OB of the right triangle ABO. They are both equal to 5 and therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles. So you can write down that AO equals to itself is a common side that belongs to both triangles. AO equals to itself is a common side that belongs to both triangles. So we actually found out that all the sides of the right triangle AMO are correspondingly equal to all the sides of this right triangle ABO, therefore those two right triangles can go into each other according to side rule. So write it down. If you follow that the right triangle AOM congruent, this is the side of congruent to the right triangle ABO according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are equal to each other. They are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, because of the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other, their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right triangle ABO must be equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus this angle that is a right angle. In total it must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABO, alpha plus beta plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation and we get that alpha plus beta equals to 180 degrees plus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We have to find out the values of angles alpha and beta. So if we focus on the right triangle ABO, we get that in the right triangle ABO sinus alpha equals to BO over AO. And again, sinus alpha equals to BO over AO. BO is, start it again, and right triangle ABO, sinus alpha equals to BO over AO. BO is 5 over AO. AO is 5 over square root of 5. 5 times square root of 5. So in total, sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled. And we left only with 1 over square root of 5. So in total, we can find out that sinus alpha equals to 1 over square root of 5. Okay, again. We can find out that sinus alpha equals to 1 over square root of 5. our task is to find out the value of alpha itself. In order to find out the value of alpha itself, angle alpha itself, we have to operate the opposite function of sinus, that is arc sinus, on the result. In this way we get the value of alpha itself. So the opposite function of sinus is arc sinus. We'll operate the function arc sinus on the result, that is 1 over square root of 5. In this way you get the value of alpha itself. You can calculate the value of arc sinus in a calculator. You get that arc sinus of 1 over square root of 5 equals to alpha, and alpha equals to 26.565 degrees. Arc sinus of 1 over square root of 5 is alpha, and alpha equals to 26.565 degrees. And therefore 2 alpha equals to 2 times 26.565, this is actually 53.15 degrees. And again, if we found out in total that alpha equals to 26.565, and therefore 2 alpha equals to 53.15 degrees. And we already found out actually that beta equals to 90 degrees minus alpha. And again, we only found out that beta equals to 90 degrees minus alpha. That is to say, beta equals to 90 degrees minus alpha, that is 26.565. And 90 degrees minus 26.565 equals to 63.345 degrees. So if we found out that beta equals to 63.435 degrees, and therefore 2 beta equals to 2 times 63 times 435 degrees. That's actually 126. 2 beta equals to 126.87 degrees. In conclusion, we found that beta equals to 63.435 degrees, and 2 beta equals to 126.87 degrees. And we already found out that alpha equals to 26.565 degrees, and 2 alpha equals to 53.15 degrees. So our task is to find out the area of this green shape. So in the next step, we join points M and B together by a straight line. By joining points M and B, actually divided the green shape into 2 segments. We have the upper segment and the lower segment. We define the upper segment as BLM, BUM, use abbreviation for upper. So the upper segment is BUM, and the lower segment, we define this lower segment as BLM. BLM. L is abbreviation for lower. So, repeat again, by joining points B and M together by a straight line, we divided the green shape into 2 segments. We have the upper segment BUM and the lower segment BLM. We calculate the area of each segment separately, and then we'll add the 2 areas together, the sum will be the area of the green shape. That's actually the area of the upper segment BUM plus the area of the lower segment BLM. So first of all, we'll calculate the area of the lower segment BLM. So what is the area of the lower segment BLM? So first of all, I will copy sector A and B. And in operation, we find out the area of the lower segment BLM. Okay, this is sector ABM. This is a copy from the original drawing. And again, this is sector ABM. But first of all, what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. Again, a sector is a portion of a circle enclosed by two radii and the arc AB between them. So what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the area of this sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is theta. The two legs are the radii AO and OB, so it is times the angle that contains the sector, that is theta, over 360 degrees. Repeat again, the area of this sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is theta over 360 degrees. So the area of this sector equals to pi r squared times theta over 360 degrees. We use this formula in order to find out the area of this sector, sector A or AMB. We know that this is the angle between the legs of the sector. Again, this is the angle that is between the legs of the sector. This is alpha plus alpha. This is 2 alpha. 2 alpha is the angle between the legs of sector A and B. We already found out that 2 alpha equals to 53.15 degrees. 53.13 degrees. 53.13 degrees. So angle A and B equals to 53.15 degrees. And the two legs of the sector are the radii of the quarter circle. That's actually 10. AB equals to 10. AM also is the radius of the quarter circle, that is 10. AM also equals to 10. So what is the area of the sector ABM? Here the rounded line above ABM is the sign for a sector. So the area of the sector ABM, according to the formula that I presented to you a couple minutes ago, will be equal to the area of the circle that contains the sector. It's actually pi r squared. R is 10 R is the radius of the quarter circle, that is 10, times the angle between the legs of the circle, that is 53.13 over 360 degrees. And again, the area of this sector ABM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 degrees over 360 degrees. R is 10, therefore r squared is 10 squared, that is 100, so pi r squared is 100 pi times the angle between the legs of the sector, that is 53.13 degrees over 360 degrees. Actually, in total, the value of this expression is equal to 46.3646 square units in its size. So in total, we found out that the area of this sector is equal to 46.3646 square units in its size. Our task is to find out the area of this lower segment BLM. So what is the area of this lower segment BLM? From the drawing, it is very easy to see that the area of this lower segment BLM will be equal to the area of the big sector ABM minus the area of triangle ABM. Again, the area of the big sector ABM minus the area of this triangle ABM will be equal to the area of the segment BLM. So with the knowledge, we found out that the area of this lower segment BLM equals to the area of the lower segment BLM of this lower segment BLM equals to the area of sector BLM, the area of sector ABM, the big sector ABM minus the area of this triangle ABM. Minus the area of triangle ABM. And again, the area of this lower segment BLM, the lower segment BLM equals to the area of the big sector ABM minus the area of triangle ABM. We already found out that the area of sector ABM equals to 46.3646 square units in its size, 46.3646 minus the area of this triangle ABM. You know that AB equals to 10, AM also equals to 10, and the angle between the legs of the sector is 53.13 degrees in its size. 53.13 degrees. What is the area of this triangle ABM? Actually, we have a special formula for a triangle. This is triangle ABC that could be any triangle. In triangle ABC, side AB equals to A units in its line. Side AB equals to A units in its line. Side AB equals to A units in its line. Side AC equals to B units in its line. And the angle between side AB and side AC is theta. Angle BAC equals to theta. The area of this triangle that could be any triangle equals to A times B, that is the sides between angle theta, that is A times B, times angle times sinus theta over 2. Again, the area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. So we use this formula in order to find out the area of this triangle ABM. According to the formula that I presented to you, the area of this triangle ABM will be equal to AB times BM times sinus the angle between those two sides, that is 53.13 degrees over 2. AB is 10 times BM is also 10. Sinus 53.13 is 0.8 divided by 2. 10 times 10 is 100. 100 over 2 is 50. And 50 times 0.8 is 40. So in total we should find out that the area of this triangle ABM is equal to 40 square units in its size. And the area of segment B and M equals to the area of sector ABM minus the area of triangle ABM. That is to say, the area of sector ABM is 46.3646 minus the area of this triangle ABM, that is 40. 46 minus 3646 minus 40 is 6.3646. 6.3646. So in total, if you want to know that the area of the lower segment B and M equals to 6.3646 square units in its size. Okay. The area of this sector B and M equals to 6.3646 square units in its size. So in the next step, we'll find out the area of the upper sector BUM. So what is the area of the upper sector BUM? But again, what is the area of this upper segment BUM? The area of the upper segment BUM that is the upper green segment BUM. The area of the upper segment BUM must be equal to the area of sector OBM. This is the area of the big sector OBM. And again, this is the area of sector OBM minus the area of triangle OBM. Again, the area of this green segment BUM equals to the area of the big sector OBM minus the area of this triangle OBM. So write it down. If you found out that the area of this segment BUM equals to the area of the big sector OMB or OBM. minus the area of this triangle OBM. Repeat again. The area of this upper segment BUM equals to the area of the big sector OBM minus the area of triangle OBM. It is very easy to see that the area of the sector OBM minus the area of triangle OBM equals exactly to the area of the green segment BUM. Okay? The angle between the legs of the sector, you see that the angle between the legs of the sector is 2 beta. And we have already found out that 2 beta equals to 126.87 degrees in its size. Here, 2 beta equals to 126.87 degrees in its size. OB equals to OM, they're both the radii of the circle, is equals to 5. OB equals to 5, OM also equals to 5. Here OB equals to 5 and OM also equals to 5. So what is the area of this sector OBM? According to the formula that I presented to you a couple of minutes ago, the area of the sector OBM equals to the area of the circle that contains the sector, that is pi r squared. R is 5. R is 5, so it is pi r squared, the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. Then again, the area of this sector OBM equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. Actually, the value of this expression, it is actually equals to 27.67 square units in its size. Again, this expression in total equals to 27.67 square units in its size. Actually, pi r square is pi times 5 square, because r is 5. So here we have 25 pi times 126.87 over 360 degrees. 25 pi times 126.87 over 360 equals to 27.67 square units in its size. So if we found out that the area of this sector BOM equals to 27.678 square units in its size, minus the area of this triangle BOM. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM will be equal to OB times OM, OB times OM, times sinus the angle between those two sides, that is actually sinus 126.87 over 2. And again, the area of this triangle OBM, according to the formula that I presented to you in the beginning a couple of minutes ago, it will be equal to OB times OM times the sinus 126.87 over 2. OB is 5, OM is also 5, so 5 times 5 is 25 over 2 times sinus 126.87, it actually equals to 0.8 and 0.8 times 25 over 2, that is 12.5. 12.5 times 8 is 10. So total we found out that the area of this triangle BOM is equal to 10 square units in its size. And the area of this segment BUM equals to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10 square units. 27.678 minus 10 is 17.678 square units in its size. So in total we found out that the area of this upper segment BOM equals to 17.678 square units in its size. And the area that we are looking for is the area of this green shape, that actually equals to the area of the upper sector BOM. That is the area of the upper sector BOM, that is 17.678 square units in its size, plus the area of the lower segment BLM. We already found out that the area of the lower segment BLM is equal to 6.3646 square units in its size. So in total, the area of the green shape equals to the area of the upper segment BOM plus the area of the lower segment BLM again, the area of the green shape in total equals to the area of the upper segment BOM. That actually equals to 17.678 minus the area of the lower segment BLM, that is equals to 6.3646 square units in its size. So the area of the green shape in total equals to the area of the upper segment BOM, that is actually 17.678 plus the lower segment BLM, that is actually 6.3646, and it is equals to 24.0426 square units in its size. So again, I should find out that the area that we are looking for in this question, this is the area of this green shape equals to the area of the upper segment BOM, that is 17.678, minus the area of the lower segment BLM, that is actually 6.3646. In total, it is 24.0426 square units in size. Repeat again, the area of this green shape equals to 24.0426 square units in size. So in the next step, I'll start the lecture. In this lecture, our task is to find out the area of this green shape. So in the drawing we have square ABCD. We know that one side of this square ABCD is equal to 10 units. Inside this square ABCD we have a quarter circle and this semicircle. Again, our task is to find out the area of this gray shape. So first of all, we define the center of this semicircle. This point is point O. We know that BC is one side of square ABCD, that is 10, but BC is also the diameter of the semicircle, that is 10. So if the diameter of the semicircle is 10, then the radius must be equal to 10 over 2, that is 5. So OB is 5, is the radius of the semicircle, that is 5. OC is also the radius of the semicircle, that is 5. And the radius of the semicircle is 5, but we know that point A is the center of the quarter circle. This is the quarter circle, and point A is the center of the quarter circle. So point A is the center of the quarter circle, point D is the point of the quarter circle itself, therefore AD is the radius of the quarter circle, that is 10. Likewise, AB is also the radius of the quarter circle, that is 10. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is 5. In the next step, we join points A and M together by a straight line. Again, point A is the center of the quarter circle, point M is the point of the quarter circle itself, therefore AM is the radius of the quarter circle, that is 10. AM is also a tangent to the semicircle at point M. Again, AM is tangent to the semicircle at point M. Point M is the point of tendency of tangent AM with this semicircle. OM is the radius of the semicircle, that is equal to 5. The radius OM, that is equal to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. Again, whenever your radius is drawn to the point of tendency, like the radius OM that is drawn to point M, then tangent AM will be perpendicular to the radius OM. If AM is perpendicular to OM, it means that this angle equals to 90 degrees. This angle equals to 90 degrees according to rule 1. In the next step, we join points O and A and O together by a straight line. We know that all the angles inside any square are right angles. This is angle ABC. That is 1 out of 4 angles of square ABCD. Must be straight. Must be equal to 90 degrees in its size. Must be a right angle. So in the next step, we prove that those two right angles can go into each other according to angle similarity rule. But before that, I copied the right angle ABO in a new page, and we implemented the Pythagoras theorem on this right angle ABO. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, this is the right angle ABO that I copied from the original drawing. AB equals to 10, BO equals to 5, and the hypotenuse AO is the missing side. So in the right angle ABO, according to the Pythagoras theorem, AO square, that is the square of the hypotenuse, must be equal to AB square plus BO square. AO is the missing side, so we left it as it is, and it is equal to AB square. AB is 10, therefore AB square is 10 square, that is 100, plus BO square. BO is 5, therefore BO square is 5 square, that is 25. So in total, AO square equals to 100 plus 25, that is 125. So AO square equals to 125. Here we substitute 125 by 25 times 5. Then we took a root out of this equation and found out that AO equals to the square root of 25 times 5. The square root of 25 is 5, so inside the root we left only with 5. So in total AO equals to 5 times square root of 5 units in its length. Again, AO equals to 5 times square root of 5 units in its length. This is side AO, that is equals to 5 times square root of 5 units in its length. In the next step, we prove that those two right angles can go into each other according to a side rule. So why those two, that is to say, the right angle ABO can go into the right angle AOM according to side rule. So why those two right angles can go into each other? First of all, AM equals to AB the above equal to 10, and therefore they are equal to each other. Actually, the above the area of the quarter circle is equal to 10, and therefore they are equal to each other. In addition, BO equals to OM, the above the area of the semicircle, and therefore they are equal to each other. And finally, AO equals to itself as a common side that belongs to both triangles. So if we prove that all the three sides of the right triangle AO and O are correspondingly equal to all the three sides of this right triangle ABO, and therefore those two right triangles can go into each other according to side rule. Repeat again. If we found out that the right triangle AOM congruent, this is the same congruent to the right triangle ABO according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So in the right triangle ABO, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees. Total must be equal to 180 degrees. So in the right triangle ABO, according to the rule that the sum of the angles in any triangle is equal to 180 degrees, alpha plus beta plus 90 degrees, total must be equal to 180 degrees. If we subtract 90 degrees from this equation, and finally found out that alpha plus beta equals to 180 degrees plus 90 degrees is 90 degrees. If we subtract alpha from this equation, and finally found out that beta equals to 90 degrees minus alpha. We continue to focus on the right triangle ABO. On the right triangle ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. Repeat again, in the right triangle ABO, sinus alpha equals to BO over AO. BO is 5, AO is 5 times root of 5. Well, we found out that BO equals to 5 times root of 5. BO is 5 and AO is 5 times root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled. After we cancel 5, we left only 1 over square root of 5. So in total, we found out that sinus alpha equals to 1 over square root of 5. And again, in total, we found out that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we will operate the opposite function of sinus, that is arc sinus, on the result. This will give us the value of alpha itself. So the opposite function of sine is arc sine, so arc sine of 1 over square root of 5 is equal to alpha. Can find out, can find out the value of arc sine by using a calculator. Arc sine of 1 over square root of 5 is 26.565 degrees. So if alpha equals to 26.565, it means that 2 alpha must be equal to 53.15 square in size. We only found out that beta equals to 90 degrees minus alpha. Therefore, beta equals to 90 degrees minus alpha, that is 26.565. So beta equals to 63.435 degrees in its side. And therefore 2 beta equals to 2 times 63.345, that is 126.87 degrees. And again, I should have found out that alpha equals to 26.565 and beta equals to 63.435 degrees. our task is to find out the area of this green shape. So what is the area of the green shape? So first of all, we join points M and B together by straight line. Again, we join points M and B together by straight line. By joining points M and B together by straight line, we divided the green shape into two parts. We have the upper segment MUB and we have the lower segment MLB. So what is the area of the green shape? So first of all, I copied sector A and B in a new page and analyze this sector. This is sector A and B that I copied from the original drawing. So first of all, what is a sector? A sector is a portion of a circle. Again, a sector, this is sector A or B. It is a portion of a circle enclosed by two radii and the arc between the two radii, that is AB. Okay. The angle between the legs of the sector, the two radii defined as the legs of the sector. The angle between the two legs of the sector is theta, and the area of this green sector A or B equals to the area of the circle that contains the sector, that is actually pi r squared, because r is the radius of the circle, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, the area of this sector A or B equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. We use the formula in order to find out the area of this sector, sector A and B. Repeat again that our task is to find out the area of this lower segment MLB. This is the small lower segment MLB, and we have to find out the area of this lower segment MLB. But first of all, we'll find out the area of this sector A and B. What is the area of sector A and B? According to the formula that is presented to you a couple of minutes ago, the area of this sector A and B will be equal to the area of the circle that contains the sector, that's actually pi r squared. R is 10. You see here that R is the radius of the quarter circle, that is 10. So it is pi r squared times the angle between the legs of the sector. This is the angle between the legs of the sector. This is alpha plus alpha, this is 2 alpha. And we already found out that alpha equals to 26.565, and therefore 2 alpha will be equal to 53.13 degrees in its size. In total, we should know that the angle between the legs of the sector is equal to 53.13 degrees in its size. So the area of sector A and B equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 over 360 degrees. R is 10, therefore r squared is 10 squared, that is 100, so pi r squared is 100 pi, times the angle between the legs of the sector, that is 53.13 over 360 degrees. So in total, the value of this expression, 100 pi times 53.13 over 360 degrees, is equal to 46.3646. So in total, if you want to know that the area of this sector A and B is equal to 46.3646 square units in its size. Our task is to find out the area of this lower segment MLB. So what is the area of the lower segment MLB? The area of this lower segment MLB. The area of the lower segment MLB will be equal to the area of the big sector A and B minus the area of triangle A and B. Again, if you subtract from the area of the sector A and B, the area of this triangle A and B, so you will remove the triangle, you will get the area of segment MLB. Repeat again, the area of this segment MLB equals to the area of sector MLB minus the area of target MLB. It is very easy to see it from the drawing. Okay, so we already found out that the area of this sector MLB is equal to 46.3646 degrees, and it's 46.3646 units in its size. This is the area of this segment A and B minus the area of this triangle A and B. AM and AB above the radius of the quarter circle that is 10, and the angle between those two sides is 2 alpha, that is actually 53.13 degrees in its size. According to the formula that I presented to you a couple of minutes ago, the area of this triangle A and B will be equal to AM times AB times sinus 53.13 degrees over 2. Again, the area of this triangle A and B equals to AB times MB times sinus angle 53.13 over 2. AB is 10, MB is also 10, and sinus 53.13 is 0.8 divided by 2. 10 times 10 is 100, 100 over 2 is 50, and 50 times 0.8 is equal to 40. So in total we found out that the area of this triangle A and B equals to 40 square units in its size, and the area of this segment MLB equals to the area of sector A and B, that is 46.3646, minus the area of this triangle A and B, that is 40. 46.3646 minus 40 is 6.3646. So in total we found out that the area of this lower segment BLM is equal to 6.3646 square units in size. Repeat again. We actually found out that the area of this lower segment MLB equals to 6.3646 square units in size. So in the next step, we'll find out the area of the upper segment MUB. What is the area of this upper segment MUB? And again, our test to find out the area of the upper segment. We already found out that the area of the lower segment MBLM is equal to 6.346 units in size. And now we have to find out the area of this upper segment BUM. The area of this upper segment BUM will be equal to the area of the sector BOM minus the area of the BOM. Repeat again. The area of this sector, the area of this segment BOM equals to the area of sector BOM minus the area of triangle BOM. It is very easy to see from the drawing that the area of sector BOM minus the area of triangle BOM will give us the area of this segment BOM. So what is the area of this sector BOM? It will be equal to pi r square, that is the area of the circle that contains the sector, the area of this circle that contains the sector, the radius is 5, so pi r square is 25 pi. This is pi r square times the angle between the sector, that is 2 beta. 2 beta is 126.87 degrees over 360 degrees. Repeat again, the area of this sector in total equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. R is 5, so r squared is 5 squared, that is 25, so in total pi r squared is 25 pi, times 126.87 over 360 degrees. So in total, the value of this expression is 27.678 square units in its size. So in total, we found out that the area of this sector BMU equals to 27.678 square units in its size, minus the area of this triangle BMU. BO is 5. Again, BO is 5. OM is also 5, and the angle to beta is 126.87 degrees. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BMO will be equal to BO times OM times sinus 126.87 degrees over 2. BO is 5, OM is also 5, so 5 times 5 is 25, and sinus 126.87 is 0.8 divided by 2. 25 over 2 is 12.5, 12.5 times 0.8 is 10. So total we found out that the area of this triangle BOM equals to 10 square units in its size. And the area of this segment BUM equals to the area of sector BMO, that is 27.678, minus the area of this triangle BOM, that is 10. 27.678 minus 10 is 17.678 square units in its size. So in total we should find out that the area of this segment BUM equals to 17.678 degrees in its size. Our test is to find out the area of this green shape. And it is very easy to see that the area of this green shape equals to the area of the upper segment BUM, that is equal to 17.678 degrees, is equal to 17.678 square inches in size, minus the area of the lower segment BLM, that is equal to 6.346 degrees in its size. And again, the area of the green shape in total equals to the area of the upper segment BUM, that is equal to 17.678 square inches in its size, minus the area of the lower segment BLM. We already found out that the area of the lower segment BLM equals to 6.346 square inches in its size. And 17.678 plus 6.3646, in total it is equal to 24.0426 square inches in size. So the answer to the question is that the area of this green shape, that is the area that we are looking for this question, it is equal in total to 24.0426 square inches in size. Okay, thank you very much.